Alright, now we're going to look at glucose transporters briefly in hypoxia. Alright, so we have glucose transporters named GLUT1 to GLUT5, which allow for glucose entry into cells. Typically, these transporters are a single polypeptide chain. It's 500 residues long, and also has a 12 transmembrane helix structure. So we are spanning the cellular membrane here. We have GLUT1 and GLUT3, and these are in all mammalian cells, or nearly all. And they are responsible for basal glucose uptake. Their Km is about 1 millimolar. This is significantly less than serum glucose concentrations, which typically range from 4 to 8 millimolar. So hence GLUT1 and GLUT3 continually transport glucose in at a constant rate. Next we come to GLUT2, which is present in the liver and the beta cells of the pancreas. Now, these proteins have a Km that is 15 to 20 millimolar for glucose. What this means is that glucose enters these tissues at a biologically significant rate only when there is much glucose in the blood. Okay, so we only get entry into these cells when there is significantly high blood glucose. The pancreas can sense the glucose level and accordingly adjust the rate of insulin secretion. The high Km value of GLUT2 also ensures that glucose rapidly enters liver cells only in times of plenty. So we only want glucose in the liver when it is abundant, because then we can make glycogen. We do not want to make glycogen if we don't need to, if we need that blood glucose. Finally, we come to GLUT4, which is present in muscle and fat cells its Km is around 5 millimolar. The number of GLUT4 transporters will increase when insulin is secreted. So this is an example of hormonal control of transcription. And translation. And this is showing how insulin will promote the uptake of glucose by muscle and fat. Okay. And now we are going to look at hypoxia. Now hypoxia is when we have limited oxygen. Okay, when we have limited oxygen, this enhances tumor growth and the reason why it enhances tumor growth is because it activates the transcription factor HIF1, or hypoxia inducible transcription factor. Right. HIF1 will increase the expression of most glycolytic enzymes In addition, it also increases the expression of GLUT1 and GLUT3 so that we can have enhanced glucose uptake. These adaptations enable a tumor to survive as new blood vessels grow. So as a tumor awaits new vasculature, it can survive in this manner because it can have increased glycolysis. And increased glycolysis results in ATP. Granted, it's a minor amount of ATP, but it's enough ATP to keep the cancer cell growing. HIF1 also results in the increased expression of vascular endothelial growth factor, or VEGF. Okay, and this facilitates the growth of new blood vessels. When oxygen is plentiful, the growth factor is hydroxylated. And this hydroxylation allows for its digestion by the ubiquitin pathway. Okay. In the absence of oxygen, the protein is not hydroxylated and it persists and promotes glucose transporters and glycolytic enzymes. So this is going to conclude our discussion of Chapter 18, and on Friday we're going to move on to our discussion of gluconeogenesis.